Okie dokie. Hopefully everyone appreciates the clickbaity title, so let's get into it. This video was prompted by my Aussie mate Scotty Storm, who drops in occasionally to leave comments that are completely unrelated to the content of the video in question. And in this case, he drops a link to JTolan Media1's claim that he can see 1,000 miles to Hudson Bay. Alright, so a very quick summary of JTolan's video. He was flying from Buffalo, New York to Chicago, Illinois, looking north out his window, and thinks that he can see Hudson Bay, which is roughly 600 miles away. Now obviously on a globe, something 600 miles away would be way below the horizon. Absolutely no chance of seeing it. So why does JTolan think he can see the 600 miles to Hudson Bay? So here is his camera location. And if you want to know how I got those coordinates, please check the video link in the description. So what he's done here is calculate the viewing angle down to two landmarks, that being the southern edge of Georgian Bay down here, which is near a place called Hope Ness. It's 135 miles away, and the second landmark is on the far side of Georgian Bay, which he says is 210 miles away, over here. And from those two landmarks, he's constructed a ruler. Now, if you know anything about image analysis, you'll know that a photo is all about angles. So every photo has a defined horizontal field of view and a defined vertical field of view. Both are measured in degrees or radians or whatever. And for rectilinear lenses, which is what most cameras have, that relationship between pixels and the angles is linear. So it is 100% acceptable for JTolan to apply a ruler to this image and then extrapolate it out to where he thinks Hudson Bay should be. And Hudson Bay seems to coincide with that dark strip up here. Obviously for normal people it just looks like a fucking blur under the cloud, and then they pay it no more attention. But for morons like Scotty Storm, this is proof of flat Earth. Right, so just a really quick example of what he's doing here. In this example, we've got him at 35,000 feet, and there is a house that's 30 miles away over the ground. To work out the angle here, we need to use the tangent function and come up with an angle of 12.46 degrees. Which is the same angle as the angle below eye level if you're looking at it from the plane. So pretty simple stuff. Now with all this data from this screenshot, we can work out a few things. So firstly, you'll notice that JTolan does not give his altitude, but we can work it out anyway because we have the angle and we have the distance. So the tangent of the viewing angle is equal to the height over the distance. We know the angle and we know the distance, so we can work out the height to be 29,875 feet. Now over here I've drawn some error bars just to show you what altitude JTolan might have used in his calculation if he slightly misplaced his ruler or used a different altitude than the one I've calculated. So for example, if he used a nice round 30,000 feet, then the angle works out to be 2.41 degrees, and there just isn't enough resolution in this image, and we'd be arguing over a pixel. Anyway, we're going to use 29,875 feet as his altitude, but just keeping in mind that it could be a couple of hundred feet higher or lower. Alright, so if we are at 29,875 feet, then the viewing angle down to Georgian Bay, 210 miles away, is given by the following equation, and it works out to be around about 1.543 degrees down below eye level. Now, if you look at his ruler over here, the 1.5 degree mark is very clearly marked before we hit the far shore of Georgian Bay, meaning that Georgian Bay itself would start with a 1.4 rather than a 1.5. And even if we give him a pretty big benefit of the doubt and use an altitude at the lower end of our range, it still works out to be greater than that 1.5 degrees. Right, so what does the ruler look like if we go and correct that angle? Well, clearly that stretches the whole ruler, and that has the effect of putting our 0.60 degree mark, which is meant to be Hudson Bay, way above that black strip. that it was originally pointing at. But it gets worse. As it turns out, it's not even 210 miles to the far shore of Georgian Bay. It's actually only 204 miles. So now we have to recalculate the angle down to the shore of Georgian Bay with the correct distance, and that pushes the 0.60 mark even higher, to the point where even giving those fluffy white clouds a bit of a nudge. And yes, it actually gets worse. Is it really 0.60 degrees down to Hudson Bay at 600 miles? Of course it's not. If you're at an altitude of 29,875 feet and something is 600 miles away across a flat plain, then the angle down to that point is 0.54 degrees and not 0.60 degrees. For it to be 0.60 degrees, your altitude would need to be around about 33,000 feet, which it obviously isn't. But if it was 33,000 feet, then your angle down to Hope Ness here in the foreground would actually work out to be about 2.65 degrees and not 2.4 degrees. So obviously that's not the case. Can it actually get any worse? Yes. Is it actually even 600 miles to Hudson Bay? Of course it's not. If you actually were to draw a line of sight in between the two landmarks that JTolan identifies in his photo, that line of sight actually hits Hudson Bay at around the 666 mile mark. So he's about 10% off. And that has the effect of even further reducing that viewing angle down to about 0.49 degrees. And if we plot that on the ruler, then we're officially into fluffy white clouds territory. So clearly that black strip is absolutely nowhere near the right spot for it to be Hudson Bay. But the big question is whether this is just a typical flurfer mistake or whether JTolan has fudged the numbers. And I'm going to go with the latter. I know JTolan is a pretty smart guy. He's supposedly a microwave engineer or something. And he clearly knows his way around the math. Yet every one of these calculation errors was an error in the favor of flat Earth. If they were accidents, then I would think that at least one of them would be in favor of the globe. So there you go. I'm calling you out, good sir. I think you deliberately fudged this to fit the flat Earth. Anyway, let's go and do it all properly. Okay, so here is the screenshot, exactly one frame before JTolan draws on it. And what I've done here is highlight 7 landmarks rather than just the original 2 that JTolan used to construct his ruler, which was Hope Ness and the far shore of Georgian Bay. I've also grabbed the Y pixel coordinate for each one of these, which means you guys know what comes next. Excel! Woohoo! Now this slide is going to take a bit of explaining. So instead of using the 29,875 feet we've been using in the first half, I'm actually going to use what I think is a more accurate altitude. And again, if you want to see how I came to this figure, please see the video link in the description. So for each landmark, I need to calculate a viewing angle down to that landmark, both for a flat Earth and a globe. With standard refraction, of course, which is what I've done in these 2 columns. So for the flat Earth calculations, it's the simple trigonometry we did earlier. For the globe calculations, it's a little more complicated, and I can't really be asked going through it in a video again. Maybe I'll leave it as a challenge for the flurfers to check the math, or maybe I'll leave a link to one of my older videos in the description that goes through those sort of calculations. Anyway, once I have all the viewing angles for both a flat Earth and a globe, this is where we get to test both of the models. So remember, the fundamental principle in photo analysis is that the relationship between these angles and the pixels is linear. So what we do here is plot the angle against the pixel, and then get Excel to try and draw a straight line through that graph. So as you can see on the left, the flat Earth angles really don't match the photo, while on the right hand side, the globe angles are quite a really good fit. And Excel can actually quantify how well they fit. There is an Excel function called RSQ, or R squared, which actually calculates a correlation figure for how well the data fits that line. And the closer that number is to 1, the better the correlation. So obviously here we have 0.9574 for the flat Earth model, which is 0.0426 away from 1. And for the globe, that number is 0.986 or 0.014 away from 1. So in one way of thinking about it, you could say that the globe model fits the photo approximately 3 times better than a flat Earth model. And that is the end.